instructional tape that was prepared pre-mission. That will begin momentarily. This is Mission Control.
The Tracking and Data Relay Satellite System, or TDRS, is designed to provide almost continuous tracking and communications with spacecraft in low Earth orbit, including the Space Shuttle. The TDRS satellites are designed to make communications between low Earth orbit and Earth as accessible as communications from continent to continent. Prior to STS-43, 3 TDRS satellites were placed on orbit by one of their primary users, the Space Shuttle. TDRS-A was placed into orbit in 1983. A second TDRS was lost in the Challenger accident. TDRS-C was launched on STS-26 in 1988. TDRS-D was deployed in 1989. And the fifth TDRS, TDRS-E, is to be placed into orbit aboard STS-43. The TDRS satellites were built at the TRW Space and Technology Group in Redondo Beach, California. After extensive testing, the satellite was delivered to the Kennedy Space Center, where it was mated to its upper stage booster, the Inertial Upper Stage, or IUS, built by Boeing for the United States Air Force. As with previous TDRS missions, the shuttle will carry the satellite to an altitude of 160 nautical miles. During the ascent and on-orbit phases, power and communications interfaces are provided via the orbiter. Once on orbit, the deploy operations will combine the use of 3 independent spacecraft, the orbiter, the TDRS, and the IUS, with 3 separate control centers and a complex worldwide communications network. The White Sands Ground Terminal in New Mexico will command and control the TDRS spacecraft through NASA ground stations around the world. The Air Force Control Facility in Sunnyvale, California will command and control the IUS using Air Force tracking sites. The Mission Control Center in Houston will provide overall control and direction for the flight using the Spaceborne Tracking and Data Relay Satellite System. After being cleared for pre-deploy operations, the crew will initiate a complex self-test sequence of IUS systems, including gimbal tests of the IUS solid rocket motor nozzle. Air Force controllers will then begin a checkout of the IUS, sending commands first through their Hawaii tracking station and then through the orbiter using the Payload Interrogator, or PI. Next, controllers at White Sands will perform checks of the TDRS, sending test commands via the Merritt Island ground station in Florida and through the orbiter PI. A critical mission milestone in deploy preparations will be the TDRS Direct Command Check. The TDRS Control Center will send commands through antenna at White Sands directly to the spacecraft, verifying its ability to receive and transmit data directly to and from the ground. For this check, the TDRS will be raised by its tilt table to 29 degrees. At this elevation, the TDRS Omni antenna will be in a direct line of sight with the ground station. After the direct check, the crew will maneuver the shuttle to the deploy attitude, and the TDRS IUS will be transferred from orbiter power to IUS batteries. The power and data umbilical will be disconnected, and the tilt table raised to 58 degrees. Just over 6 hours into the mission, the 19-ton payload will be ejected at 1/2 feet per second from its tilt table and out of the cargo bay. 1 minute after deploy, the crew will perform a 2.2 feet per second orbiter maneuver to maintain good line of sight with the payload as they separate. 15 minutes after deploy, the crew will fire the orbiter's OMS engines to move the orbiter off to a safe distance before the first stage IUS motor is fired. 1 hour after deploy, the first stage engine will ignite, propelling TDRS into a transfer orbit with an apogee of 22,500 miles. The TDRS IUS will coast for about 6 hours before reaching apogee, where the first stage will separate, and the second stage will fire to circularize the satellite in a geosynchronous orbit. Shortly after reaching its operational orbit, the TDRS will separate from the IUS second stage booster. The first command sent to the TDRS will cause the satellite's twin 150 by 150-inch solar wings to deploy. Once unfurled, the satellite will measure over 50 feet from end to end. Next, the satellite's space ground link will be activated, and antennas are deployed. A long period of intensive testing will follow to prepare it for operations. With 2 operational satellites and 2 on-orbit spares, TDRS-E will greatly enhance the TDRS satellite communications network. Earthbound tracking stations used during the Mercury, Gemini, Apollo, and Skylab programs could provide communications with orbiting spacecraft for only 15% of each 90-minute orbit. With the TDRS, coverage is extended to over 85% for up to 26 users at a time. The heart of the TDRS system lies just east of Las Cruces, New Mexico, at the White Sands Ground Terminal. Here at the WSGT, 3 60-foot dish antennas distinguish the main ground link between TDRS relay satellites in space and ground-based operations facilities. Technicians at the WSGT are primarily responsible for controlling and commanding the TDRS spacecraft and the TDRS system. They also provide direct spacecraft data to and from TDRS customers, including the transmission, reception, formatting, and combining of complex signals that carry tracking, telemetry, and command information to and from the TDRS satellite, as well as users of the relay system. The NASA Ground Terminal, or NGT, located in the same building with WSGT, is responsible for processing and transmitting NASA spacecraft data to various NASA facilities via the NASA Communications Network, or NASCOM. During shuttle missions, the TDRS provides for simultaneous uplink and downlink of voice, video, and digital data between the orbiter and mission control using 2 geostationary TDRS satellites, one at a time. Downlink from the shuttle consists primarily of telemetry, such as tracking data, spacecraft systems information, and the status and results of payload and experiment operations. Ground controllers rely on uplink transmissions to command orbiter and payload systems when needed, and to transmit hard copy messages to the crew. TDRS accommodates shuttle communications in 2 bandwidths, S-band and Ku-band. S-band uplink includes ground commanding and voice, plus Doppler and ranging signals for tracking. S-band downlink signals include voice, orbiter telemetry, Doppler and ranging return signals, as well as low-rate main engine data, recorder data, and payload data. The Space Shuttle sends and receives S-band transmissions using 4 antennas located under the protective blankets around the orbiter crew compartment. These S-band antennas are omnidirectional and can transmit and receive no matter what attitude the shuttle is in. Ku-band transmissions carry a higher quantity of information. The Ku-band has 3 channels for relaying bulk information, such as a high-rate payload data, ops recorder data, television, and Spacelab data. It also carries the same voice and telemetry carried on S-band channels. The Space Shuttle communicates Ku-band signals using the Ku-band antenna, which is located on the forward, starboard corner of the shuttle payload bay on a deployable assembly. Once on orbit, the Ku-band antenna dish is deployed. Unlike the S-band, the orbiter Ku antenna requires directional pointing to communicate with the TDRS. The TDRS must be in direct line of sight with the Ku-band antenna. Ku-band contact with the shuttle can sometimes be interrupted when the orbiter's body blocks the antenna's direct view of a TDRS, or when radiation-sensitive instruments in the payload bay require antenna pointing angles to be limited. In these cases, Ku-band coverage is temporarily lost until the antenna dish is brought back in line of sight with the TDRS spacecraft. The WSGT can currently manage 2 TDRS satellites simultaneously, but in the future, demands for TDRS communications support will exceed the current capacity. So the second TDRS ground terminal, or STGT, is being constructed near the WSGT. The second terminal is scheduled to become fully operational in 1993. The second terminal will ensure TDRS coverage for all future space demands. The TDRS system virtually covers the world. TDRS user spacecraft will never be out of touch with controllers for more than a few minutes every orbit, as the network continues to provide communications essential to low-orbiting spacecraft for the space programs of today and tomorrow.